Okay, let's resume our studies on discrete distributions. This time we're going to learn a new distribution. Here we have geometric distribution. Remember, a binomial distribution basically models the total number of success events over n trials, n identical and independent trials. Okay, now let's switch the subject. We don't want to study the total number of success. Instead, we want to know when we will get the first success. Okay, that's likely also an interesting subject, right? Not only we want to know how many times we are able to achieve success, now we also want to know when we will get our first success outcome, okay? So let's introduce a random variable, okay? So now we have this x, which is called a geometric distribution if it satisfies this property. So basically the probability function of a geometric distribution is rather given in this form, okay? First, let me mention one important thing, that is it goes to infinity. Which means, let's consider a coin example, okay? Let's say the success is head. It is possible that in every in every tossing, I get tail, right? And it continues, it does not end. So although that's really unlikely, but I cannot rule out the possibility of it, right? So it's possible that I never see a success event because I am so unlucky. I'm keeping getting the result of tail. Okay, that's possible. So that's why here the possible values of x is 0, 1, 2, all the way to infinity. Remember, in the binomial case, x goes from 0, 1, 2, all the way to n, because I only try n times, right? So the maximum possible number of success is the total number of trials, so which is n. But here, I keep trying until I get the first success. And if I am a super unlucky person, I have to try infinite many times, right? So that's why here x goes from 0 to positive infinity. It does not end, okay? So this is the definition of it. From the definition, what can we see? 1 minus theta, this is the failure probability. We raise the power to x times by theta. So in other words, in this definition, this random variable x actually has a meaning. It is the number of failures before the first success. So there are two keywords. The first one is we care about, or we model the number of failures, and it is before the first success. So we can draw this kind of like a box. You know, I usually draw a box when we have discrete scenarios. So what do we have? We have failure, 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 all the way to x. So we have x failures until we get the very first success. So what is the probability? The probability for failure is 1 minus theta. I have x of them, they are independent, so I simply raise the power. And finally, in the x plus 1 position, or in the x plus 1 trial, I get a success. The probability is theta. So that is why I have this probability, right? So if you really understand the meaning, there's really no need to memorize, right? Every time when I introduce a new distribution, I'm trying to give you the actual mathematical reasoning behind it. Mathematicians do not simply introduce something for fun. They introduce a concept, introduce a definition because there is a need. There is a particular reason behind it. And that's why I'm trying to at least to convince you the reason behind those definitions, okay? But keep in mind, in actuarial science, people are not that strict in mathematics. So it's common that people just introduce definitions. Okay, they don't talk about why. For instance, in our textbook, this is how geometric distribution is defined. There's no reasoning behind it, right? So here I'm giving you the reasoning. If you truly understand the reason, you will be able to write down the probability function 10 years from now. Okay, if you just memorize, you will forget this in 3 months. Okay, probably even before we end this course. So I guess so. That means knowing the true reason behind each and every distribution is truly important. So by the way, we do have an alternative definition, not exactly alternative. Some slightly differences here. So in our default setup, we model the number of failures before the first success. So it is possible that I am so lucky. My first trial is a success. I do not wait any failures. So my wait time starts with 0. Okay. But if I model the total trials before the first success, it always starts 1, right? It needs at least one trial for me to get 1 success, right? So in this case, what I model is the number of trials before the first success. So at the first success. So here, so here is basically in this alternative definition, what we model is actually x plus 1 in this case. So that's the reason why we will need to start with 1, okay, instead of 0. And here, what we have is x minus 1 instead of x, okay? But in this course, we do not use this. We only use definition 18. I point out this possibility that is because in some other textbooks, you may see this, okay? And don't get confused. It's pretty much the same thing. Only depends on the slight difference on how you record. We also have some properties, and some of them are straightforward to confirm. Some of them are slightly more difficult. The first one is easy. The first one is quite easy. 1 minus theta to the power of x times theta. Okay, theta is a constant. Let's take it out. This is a geometric series. By the way, that is the reason why this is the name is geometric distribution, because what we have here is a geometric series. So by the definition, 1 minus the common ratio, which is 1 minus theta, and on top on the numerator is the first value of the series, it's 0. 1 minus theta to the power of 0, which is 1. So theta over theta is 1. So it's confirmed. It's what we believe, right? Adding up all the possibilities, we should get 1. So exactly it is. Next, we want to know the expectation and variance. Usually, expectation is easy to understand. Often, you can use intuition rather than mathematical proof to get this result. Let's do a little bit naive reasoning or intuition behind this result. So let's assume theta is 50%. So the chance of seeing success and failure has the same probability, half. How many times, okay, would you expect to wait before you see how many failures would you expect to see before you see the first success? Right. The number is exactly 1, because seeing a success and seeing a failure have the same probability, right? So they are equally likely. So in that sense, the waiting time is 1, right? Because it's the same, okay? In another scenario, let's say theta is 25%. So which means it's 3 times more likely to see a failure event than a success event. In this case, how many times of failures do you expect to see before you see the first success? My result is 3. because it's 3 times more likely to see the failure. So it's 3 over 1. How do I get that? It's 75% over 25%. That's exactly the reasoning behind that, right? So it's the probability of seeing a failure over the probability of seeing a success event. But of course, we can actually prove this without. Let me get a page to write down some mathematics. Okay, it's optional. So it's meaning it's nicer if you know, but if you really don't know, that's okay. You can, like many say, you can treat that as a result. You just need to memorize, right? Unfortunately, that's usually what the study manuals suggest you to do. Right? They have hundreds of formulas they ask you to memorize. From my personal point of view, there's really no need to memorize anything. If you already know, you know. If you don't know, you memorize. Okay, so I'm trying to show you the result. To prove, always start with definition. Goes from 0 to infinity. Okay, x times the probability. Probability is 1 minus theta times x times theta. Okay, now how can we solve this? This is actually a calculus question, right? So you, technically speaking, you should have seen this somewhere in your calculus course. There are different ways to solve this. One possible way is, so first of all, theta is a constant, right? So it really doesn't matter of theta. So you can take out theta if you want, and I can start with 1 because if x is 0, it is 0. Okay, this is not an easy summation to do because I have x in front, right? So if there's no x, it's so easy, right? It's just a geometric. Now with x, well, it's somehow non-trivial, right? So we need a little bit effort to do this question. So now what I want to do is I introduce a function. Okay, so this function is from 0 to infinity 1 minus theta to the power of x. Okay, of course we know this, right? So by the definition, this is the sum of a geometric series. We know this is 1 over theta, right? Which we just did, right? Okay. Obviously, this is differentiable as long as my theta is not 0. Right? It is undefined when theta is 0. Right? For anything non-zero, this is well defined and is differentiable. Right? So it has 2 definitions. Right? So the first definition of G is this infinite sum. Okay. The other definition is 1 over theta. So I differentiate on both hand sides. Let's start with the right hand side because it's easier. So you can write this as negative power, right? So when you differentiate, what you get is 1 over theta squared. Okay, on the right hand side, let's assume I can switch the order, meaning I can differentiate the inside first. So this is not complicated, right? It's a power function, and it's a function of theta, meaning I'm going to treat x as a constant. So that's why it's a power function, not exponential type. Okay. So now what do I have? So in this, by the way, because of the chain rule, I do have a negative. Okay, because inside is 1 minus theta, so I have a negative. So let's do a little manipulation of the second term. Okay, in the second term, what I have is take out the negative sign. What I have is from 0 to positive infinity, it becomes x times 1 minus theta x minus 1. Okay. What we want, it's somehow, now we need to do a quick comparison, right? It's close, not exactly the same, right? The power term differs by 1. So Well, let's get it. Let's get what I want. Okay. In order to get that, I need to times by 1 plus theta, right? Because the difference here is x minus 1, here is x, right? It's short by 1. So I add 1, but I cannot obviously, change the value, which means I need to add theta, right? Which means I multiply this term by 1, so I do not change anything, right? It's the same. Okay. So what I have will be negative from x 0 to 1. So now what I have is to the theta. Okay. What's the remaining part? The remaining part will be from 0 to infinity, and I will have x times the x times theta x 1 minus theta x minus 1. Okay, that's the is that the result? Let me pause for a second and go back to this. Okay, let's resume. I noticed some small issues, so let me erase this. There are a few issues. So it's not expanding that way. It's actually goes from the value of x. So I need to do a little manipulation from there. So here, okay, I start. So the starting value is x, right? So obviously x, when x is 0, this term is 0. So if I use the blue color, so this is the same as x starts with 1, right? Because when x is 0, it's 0 times something. So it's 0. So what I can write is I start with 1 minus theta x minus 1. Okay. Now let's do a change of variable. What variable we use? Let's use y. Let y be x minus 1. Okay. Then what do I have? Because y is x minus 1, so my y will start with 0. So my x will be y plus 1. Then this is y. Okay. So let me expand this. So y from 0 to infinity, y times 1 minus theta to the power of y minus summation from 0 to infinity, 1 minus theta to the power of y. Okay. Now, if you want, you can change back y to x if you want. Okay, so that does not hurt anything. Okay, so now we can see this is exactly what we are looking for, right? So let me keep writing. So we have this. This is something we are trying to solve. Okay, minus. Okay, the other term we already know. It's a geometric series, right? So we already know this is nothing but theta, right? So now we know this entire guy. This is the results we are trying to calculate. So now we have, so finally we have the expectation is theta times this guy, which will be theta times, what do we have? We have moved this to the other hand side. We have right. So eventually we will be getting theta times theta squared. Here is 1 minus theta. So it's 1 minus theta over theta. Okay, so this proves the expectation is indeed 1 minus theta divided by theta. Okay, as you can see, this is not entirely trivial. That's why I say this is optional content. If you like, I already used some intuitions to derive this result. Why it is 1 minus theta over theta. The actual proof is rather technical, right? And to show the variance is even more complicated. For the variance part, okay, what we consider is actually this. In order to show the result, it's actually more convenient to consider this, because from this we can write. Okay, we already know the result of expectation, right? So if we are able to figure out the left-hand side, we know the second moment. From the second moment, we know the variance, right? So please give it a try on this, okay? That means you work with something similar down here, but you need to differentiate twice. So when I differentiate twice, what I get? I get x times x minus 1 minus theta x, right? Negative, negative, it's 1. So you can start with 1 if you want. Okay, so that's why that is the reason I want to consider x times x minus 1, because it's more convenient to study that. Okay, you need the second derivative to help you study. Of course, differentiate this again is very simple, right? It's nothing but 2 over theta cubic. Okay. But we do have alternative ways to prove. The alternative way is through the through MGF is a possible way to figure it out. In order to show the MGF, you need to go through the definition. So that's why usually MGF is more friendly, because it's in exponential type. So MGF is actually way easier to study, because I have an exponential term. 1 minus theta to the power of x. Okay, so what do I have? I have theta, factor it out. I collect like terms. So what I have will be 1 minus theta times exponential of t, and then with everything to the power of x, right? So this is a geometric series, right, with different base. So the summation will be 1 minus the common ratio times the first value, plug in 0, which is 1 minus theta. Okay, so that is what we are going to get for the result, right? When x is 0, oh, my mistake. When x is 0, this is 1. This is 1. Because we are talking about the 0 for x, not 0 for t. So this is the MGF. Okay. If you want, you can write this in negative power if you want. So if I want to differentiate what I get, I will be getting, if you write this in negative power, right? Okay, we can differentiate, we get a negative in front, and this entire term becomes -2. And then by applying a chain rule, we will get -1 times 1 minus theta times e to power t. Okay, now let's take t to be 0. Negative and negative will be canceled, right? So you have theta, 1 minus theta. Okay, so what's inside? When t is 0, exponential term is 1, so inside it becomes 1 minus bracket 1 minus theta bracket, so it's theta to negative 2. Okay, that's it. So it will be 1 minus theta over theta, right? Like I claimed, deriving MGF is usually a lot easier than working with the moment. In particular, the law moments, those are not easy. Once we have MGF, it's rather straightforward, right? Okay, you can differentiate again to get the second moment, then you will have the variance. Okay, from MGF to MGF, it's even easier. You replace exponential of t by t. Okay, this form is easy, right? So that's the whole study for geometric distribution. Let's mention the next one is negative binomial. Okay. Again, let's start with the reason behind introducing this definition. A geometric distribution models the number of failures before the first success. Okay, but what if I want to know the number of failures before the r's success instead of the first? Okay, so I want to study something slightly more general. Okay, I don't just want to study the first success. I actually want to study the r's success. Of course, r can be 1, can be 2. Okay, in fact, r can be even non-integer. Okay, although it's slightly unusual to see that from the general understanding, but we can if we want. So if that is our purpose, okay, we're going to need a new random variable. That new random variable is a negative binomial. Okay, it has 2 parameters. The first parameter r refers to the r's success. Theta is still the probability of success in each trial. Now I want to record, or I want to model the number of failure events before I see the r's success. Okay, so this is the rather complicated form of probability function. Again, let's draw a box. Okay, I want to see r's success, and I want to know the number of failures before this particular success. That means the last one must be a success, right? Otherwise, everything falls, right? It cannot be the case that the last one is a failure, right? Because we want to see the r's success and we want to know the number of failures before it. If we have already observed r's success, we don't care about what's happening after that. So the final result must be a success event, and this is exactly the r's success, right? R's successful event. Okay, then I will need to figure out the remaining part. Okay, if this is the r's, in front I have r minus 1 success total, right? So this is a number, not cardinal. So in front I have r minus 1 successes. Okay, how many failures? That is x. That is something I'm trying to model, right? Now it boils down how I'm going to arrange, right? So first of all, I know that the total boxes, okay, will be r minus 1 plus x, right? And among x plus r minus 1, x of them are failure. R minus 1 of them are success, okay? So it boils down how I arrange them, right? Again, I don't care about the order, okay? So it's a combination number, right? And this is exactly the combination number, right? So here I'm selecting the positions for the success events. The remaining will be the failure events, okay? So I'm selecting r minus 1 positions for the success events out of x plus r minus 1 positions. Okay. So in total, I have x failures explaining this term. Okay, 1 minus theta is the probability of failure. And here I have x failures, so the power is x. Okay, I have a total of r success events. And the probability for each one is theta, so I raise the power to r, right? So that's the meaning. So if you really understand the meaning of binomial, you can write down the probability function anytime, right? It's a simple analysis of scenarios, right? In particular, if r is 1, that's geometric, because when r is 1, this is 0, right? So it becomes select 0 out of x. So this is 1. So that goes back to the geometric. So geometric is a special case of negative binomial when r is 1. Here, the first result is rather straightforward, right? We know the number of failures we need to wait for the first success is 1 minus theta divided by theta. Now we are waiting for r success events. What would you guess, right? So it's simply times by r because everything is homogeneous, right? We are repeating identical and independent trials. If waiting for one success, we need about 1 minus theta divided by theta failure events. Now we want to wait for r success events. We simply times by r, right? And it's not surprised to see the variance is also in multiplier. Again, because of the independence, right? So everything becomes easier, okay? And we already derived the MGF, right? So this is nothing but the MGF of a geometric raised the power to r. Okay, we already know this result, right? So if we have independent random variables, in order to figure out the MGF of the summation, we simply raise the power, right? So here we want r, so we raise the power to r. So basically, another way to understand the negative binomial is that you sum up r geometric. So when you sum up I from 1 to r geometric, you get a negative binomial. Okay, with this, of course, here they are identical and independent, right? With this in mind, everything becomes nothing but easy, right? If you consider expectation, you times them together. If you consider variance, you still times them together because they are independent. If you consider MGF, you raise the power to r. If you consider PGF, you do the same thing, right? So, but of course, you can also apply mathematics to study, meaning you can and you definitely should try. Okay, we also know here for x it can be, so we know the probability is x plus r minus 1. Here it's r minus 1. My success, I have r success events, I have x failure events, right? Technically speaking, you can, okay? I will leave this to you, okay? Give it a try. I think this is not entirely that tough, okay? Here the trick is to manipulate the combination number, okay? I leave that to you, okay? I will post the mathematical results on Husky CT in case you want to know more. I will stop here and leave the last one to the final video.